Hi everybody, welcome back to our next topic today in physics. So we have pretty much finished our discussions about gravitational fields, and what we want to focus our attention on for the next couple days are going to be electric fields. But before we get into the idea of fields, we have to talk about electric charge and the forces that are involved, and then we'll talk about the energies and the fields that are arising from those. Um, so we'll start with, again, the most basic thing, this idea of electric charge. Uh, and there's a lot of parallels, I'm going to kind of keep referring back to this, between charge and mass. So both of these things are a property of matter. So matter has charge and matter has mass. Um, and so it's something that's kind of inherent to that particle of matter. But unlike mass, there's two types of charges. And so generally, those two different types are denoted as positive and negative. Um, there really isn't any sort of significance to positive versus or positive and negative. It could have been up and down, left and right. All that matters is they're actually opposites of each other. Um, and by convention, the things that we know of that have charges, like on the smallest level, again, atoms are made of things that have charges. And so, for instance, by convention, electron is given a minus charge and a proton is given a positive charge, but there again really is no sort of rhyme or reason to why that was. Um, it's just the fact that they're opposites. So that's all that's really important. So again, you can call them up and down, left and right. You can even reverse the positive versus negative, but since the entire world considers the electron to be negative, the proton to be positive, I'm going to stick with that convention, and we'll do that in mind. So again, this electric charge, as I said, is a property of materials. So every object is going to have a different amount of charge kind of related with it, just like different objects have different amount of mass related to them. And so let's try and quantify this, and how can we measure it? And so the real way to do this is with the Coulomb. So the SI unit, or the International System unit for charge, is the Coulomb, named after one of the scientists who really worked on the idea of electric charge to begin with. Um, and so the Coulomb is our sort of base unit. So 1 Coulomb is a certain amount of charge, just like 1 meter is a certain amount of distance, or 1 kilometer is a certain amount, or sorry, 1 kilogram is a certain amount of mass. Um, but a Coulomb is actually quite large. So if we look at what's called the elemental charge, that's like the smallest normal charge you're going to find in the universe. It's on a proton. And so the charge of 1 proton is really, really small, 1.6 by 10 to the minus 19 coulombs. So it's quite small. But the nice thing is an electron precisely balances that charge. As I said, they're opposite of each other. And so the electron charge is negative 1.6 by 10 to the minus 19 coulombs. Another way to express that is, with that typo there, let me fix that. Um, it's not 1 Coulomb equals that many coulombs. That doesn't make any sense. It's 1 electron. Um, oops, is that many coulombs. So the charge of 1 electron is that many coulombs. So again, you can see it's a, no, I did that. That's backwards. Sorry about that, guys. Going too fast here. That makes more sense. So 1 Coulomb represents this many electrons. So if I have 6.24 by 10 to the power of 18 electrons in a group, that group would have a charge of 1 Coulomb. And so why do we care? Of course, because we know that the things that have charge can exert forces on each other. And the way we're going to talk about this thing is something called Coulomb's law, named after, again, the same guy. I think it was French Charles de Gaulle Coulomb, I think his name was. But anyways, he discovered, or certainly played with the idea that charges exert forces on each other. Um, and so two things that are close to each other that are charged will actually influence each other, either an attractive or a repulsive force. And this is different than gravity, because again, gravity will only be attractive. But electric charges, this so-called electrostatic force, can actually be attractive or repulsive. But the magnitude of the force is given by this expression here. And before we start, going too much further into some calculations, let's define these terms and then look at the sort of the similarity between this and gravity. So we'll start with, again, of course, F, that's the force. K is another constant called Coulomb's constant. His name's going to pop up all over the place here. Um, and it's given by that value. So again, that's another one of those constants of the universe. Coulomb's constant, it tells you how strong the electric force actually is. Q are going to be the two charges. So you're going to see lowercase or capital Q, like you'd see big M or little m for masses. And R, of course, is the separation of the charges. And we're going to use that in meters. And so if we look at this expression, this guy right here, and compare it to our expression for gravity. So maybe I'll do it down here. The force of gravity we talked about earlier is equal to gmm over r squared. And so these two expressions look very similar. The only difference is we're going to use a different constant, and instead of looking at mass, we're looking at charge. So that's pretty cool. The fact there's some symmetry there in the universe, but certainly not where the end of the symmetry in the universe, but not something we're going to talk about too much right now. But so there's certainly something cool where we see some patterns there. But the other thing that's important here is that the direction of this force, just like in gravity, connects the center of the object, so center to center, just like gravity did. But since we can have positive or negative charges, we have to worry about what does that mean. So if the charges are opposite, which means our force in this case will, in this expression at least, will be negative, that means our force is attractive. And if the charges are similar, so both positive or both negative, the force is repulsive. And so what that means is that in this case, F will turn out to be positive, and these things will repel each other. Um, so there's that. That's Coulomb's law. So just before we finish off, let's take a look at a couple examples here. So we'll start with something pretty neat, the idea of hydrogen. So again, you know what hydrogen looks like, I hope, that you've got a proton and, of course, an electron swinging around it. Um, we'll talk a little bit later on, of course, it's not a circle. Hopefully, maybe from chemistry, you know that it's really not close to a circle. But I'm kind of jumping ahead of myself here, but let's just pretend it is for right now. But anyways, the average radius of the hydrogen atom, meaning the distance from the center of the atom to the outside of the atom, so from here to here, on average is 53 picometers. And what the heck is a picometer? Well, pico means 10 to the minus 12, so this is also 53 by 10 to the minus 12 meters. So a very, very small distance, of course, but so these things are close together, but of course these charges are there, and so we want to see what sort of force is there, what sort of attraction is going on between the positive and the negative. And so, you know, these are charges, so we're going to be dealing with Coulomb's law, and so we'll deal with the electric charge here, so K, Q1, Q2 over R squared. Well, there's R, right? We've got R right there, 53 picometers. But of course, we have to put it in SI units, so it'd be 10 to the minus 12 meters. And for the charges, well, this is an electron and this is a proton. So just like every electron has an identical mass and every proton has an identical mass, they also have identical charges. So every electron again in the universe has the charge of the electron, that minus 1.6 by 10 to the minus 19 coulombs. And every proton in the universe has the charge of positive 1.6 by 10 to the minus 19 coulombs. And K again is that constant, that Coulomb constant, the constant of the universe. And so we're just going to plug it into this question. And again, I can trust you guys can do this, but I'm getting 1.8 by 10 to the minus 8 newtons. Sorry, 8.2 times 10 to the minus 8 newtons. Wrote the right thing, but said the wrong thing. Pardon me there. So it's a very, very small force in terms of everyday sort of examples. But in terms of an atom, that is quite a large force, because think about how small these electrons and protons are. We'll come back to the idea a little bit later on and see what sort of accelerations these things can cause. All right, so there's one example. The next one, again, I have a mystery particle, and I want to know what its charge is. And all we know is that when I put it 3.2 meters away from another one, this object that has a charge of 3.4 coulombs, it's experiencing a force of 120 newtons to the right. So that's what we know when I want to know what is that charge of the mystery particle. So again, what I'm going to ask you to do here is try this one. So pause the video for me, try this question. And when you think you've got an answer you're happy with, start the video again and we'll see how you did. All right, so hopefully you're back, and again, you've got an answer for me, and you feel like you're confident in that. And again, I really hope you have done that and you're not just, I don't know, lying to me here. But so again, we're going to go back to our expression for Coulomb force. So K, Q1, Q2 over R squared. Well, what we've got everything except for Q2. We don't know the charge of that other object, or QM, I guess we could call it. So we do a little bit of rearranging, and so we get the charge of Q2 is R squared F divided by K Q1. So that's 1. And now it's just a matter of plugging your numbers in. And again, I'm getting a charge of 4.02 by 10 to the minus 8 coulombs. So let's just pause and look at this number for a second and see if we can figure out what it means. So we said that this thing is moving to the right, and this particle, the original particle, has a charge of 3.4 coulombs. It's a positive value. And we're also getting our charge down here being a positive value. What would that mean? That would mean that these objects should repel, because positives and positives should repel each other. Look at our forces here. Our force is actually a repulsive force, so it does fit with our expectation. How would we have to change this question, though, if this were an attractive force? So notice the magnitude of the force, this idea F here, is all that we can get from this equation. So we'd have to really be concerned with ourselves about sort of attractive versus repulsive, because we said by convention, if I go back here to, yep, this one here, if the force is repulsive, we're going to be using F is positive. So we didn't think about it in this question, but it actually turned out to be the correct way to do it, because we have to be concerned about that. So it's not a left versus right or up versus down for this this idea of positive versus negative forces. It's going to be attractive versus repulsive. But again, common sense sort of check at the end, we realize that this positive charge does match with our expectations. And so I think we're pretty confident in our answer here. All right, so that's about it out of me for today. Bit of a short one. I hope that this makes sense for you. And of course, if anything's not clear, we'll talk about this in class tomorrow. Everybody have a great night.